You know how hot molten metal is. It glows red, then white, and can melt almost anything. The hottest metal on Earth, tungsten, starts melting at around 3,422 degrees Celsius. But that's just a winter breeze compared to the core of our sun. Deep inside our star, temperatures reach an unbelievable 15 million degrees Celsius, more than 25 times hotter than what it takes to melt the strongest metal known to humans. What's happening in there, and why does it matter for life on Earth? How hot is the sun's core? We often think of the sun as just a glowing ball in space, but deep inside it's a nuclear furnace so extreme that nothing could survive even close to its center. Key facts. The core temperature of the sun is about 15 million degrees Celsius. This is where nuclear fusion happens. Hydrogen atoms fuse into helium, releasing massive amounts of energy. The pressure at the core is 250 billion times greater than Earth's atmospheric pressure, enough to crush any known material instantly. How does it stay so hot? Due to the immense gravitational force, particles are compressed and accelerated to incredible speeds. These collisions generate heat and keep the sun burning for billions of years. Shocking truth. If you placed any material from Earth into the sun's core, it wouldn't just melt. It would vaporize instantly before even touching the surface. How does this energy reach us? Even though the sun's core is unimaginably hot, we don't feel that heat directly. Instead, energy has to travel through layers of dense plasma, taking thousands of years to escape, before finally reaching us in just over 8 minutes. The journey of a photon. Core, radiative zone. Photons bounce between atoms like light in a foggy mirror. Takes thousands to millions of years to pass through this layer. Radiative zone, convective zone. Energy begins to move with rising currents of hot plasma, like boiling water in a pot. Heat rises, cools, and falls again. Convective zone, surface, photosphere. Energy finally escapes into space as visible sunlight. Once free, it travels at light speed, reaching Earth in just 8 minutes and 20 seconds. A fascinating comparison. A photon born today in the sun's core may not reach the surface until the human race no longer exists. Why does this matter for life on Earth? Without the extreme heat and pressure in the sun's core, none of us would be here. The fusion process creates not only light and heat, but also the conditions necessary for life to exist. The power behind life, hydrogen to helium. Every second, the sun converts 600 million tons of hydrogen into helium. Light for photosynthesis. Plants use sunlight to create oxygen and food, the base of Earth's entire ecosystem. Stable climate. Just the right amount of heat keeps Earth warm enough for liquid water, the key ingredient for life. The perfect balance. If the core were slightly cooler, fusion would stop, and the sun would go dark. If it were slightly hotter, the sun would burn out too quickly for life to evolve. We're alive because the sun hits the sweet spot. Perfect heat, perfect timing. What if the sun changed slightly? Too cold, no fusion, no light or heat. Earth freezes too hot, fusion burns faster, sun dies sooner, no time for evolution. Just right, allows life to thrive, for now. How does the sun compare to other stars? Our sun isn't the hottest or coldest star in the universe. It sits perfectly in the middle, making it ideal for sustaining life. Let's compare it to other stars in the galaxy. Red dwarf stars, small and cool. Core temp, approximately 3 to 4 million degrees Celsius size. Smaller than the sun lifespan, hundreds of billions of years. Downside, often flare violently, dangerous for planets nearby blue giant stars. Huge and super hot core temp, over 50 million degrees Celsius size, massive, hundreds of times larger than the sun lifespan. Only a few million years end, explodes as a supernova, creating heavy elements like gold and uranium. Stars like our sun, the Goldilocks zone core temp, 15 million degrees Celsius lifespan, about 10 billion years, perfect for life, stable, long-lasting, and capable of supporting planetary systems. Why we search for sun-like stars. When scientists look for alien worlds, they focus on stars like our sun, because only these stars offer the stability needed for life to evolve over billions of years. The sun's core is a nuclear engine unlike anything else in the solar system. At 15 million degrees Celsius, it powers every living thing on Earth and makes life possible. But it's also a reminder: we live on a fragile planet, orbiting a star that will one day die. What would happen if we could recreate the sun's power on Earth? Could we build a mini-sun for clean energy? Or should we prepare for when the sun eventually fades away? If you want to uncover more secrets of the universe, don't forget to subscribe to Universe Vault Project and hit the bell so you never miss a new episode.